We discuss capacitors in network in this lecture. An electric circuit is a collection of objects. It usually contains a source of electric energy, such as battery, and we connect the battery to elements that convert electric energy to other forms. A circuit diagram can be used to show the path of the actual circuit. We use those symbols for capacitor and battery. Note the difference between capacitor and the battery. Capacitor, the two are equal lengths. For battery, we have a positive and a negative terminal of battery. Positive terminal is longer than negative terminal. This example shows two capacitors connected in parallel. The left plates of the two capacitors are connected to the positive terminal of the battery. The right plates of the two capacitors are connected to the negative terminal of the battery. In such case, we call capacitor C1 and C2 are connected in parallel. If we have two capacitors that do not carry charge initially, we connect them to battery in parallel. The charges will flow. Positive charge will flow to the plates that are connected to the positive terminal of the battery. Negative charge will flow to the plates that are connected to the negative terminal. The capacitor will reach their maximal charge when the flow of charge stops. After the maximal potential are reached on both capacitors, capacitor C1 and C2 will have the same potential difference across their two plates. And the potential of capacitor C1 and C2 equals to the potential of the battery. Capacitor C1 would carry charge C1 times delta V. Capacitor C2 will carry charge C2 delta V. The total charge on those two capacitors in parallel is the sum of charge carried on C1 and C2. So total charge Q equals Q1 plus Q2. The equivalent capacitance of a parallel combination of capacitors equals C1 plus C2. If we have more than two capacitors, then the equivalent capacitance would be equal to the sum of the capacitance of all capacitors in parallel. This example shows two capacitors C1 and C2 connected in series. For such a connection, the positive terminal of battery connected to the left plate of C1. The right plate of C1 is connected to the left plate of C2. The right plate of C2 is connected to the negative terminal of the battery. When a battery is connected to those two capacitors in series, electrons are transferred from the left plate of C1 to the right plate of C2 through the battery. So we have negative charge accumulated on the right plate of C2. The negative charge on the right plate of C2 will induce the same amount of positive charge on the left plate of C2. which will then leave the right plate of C1 with same amount of negative charge. So after the moving of electric charge stops, all the right plates of C1 and C2 will have negative Q charge, and all the left plates of C1 and C2 will have positive Q charge. We can also replace two capacitors in series by an equivalent capacitor with the equivalent capacitance CEQ. For two capacitors connected in series, the amount of charge on each plate of C1, C2 are equal. The potential difference over C1, let's call it delta V1, and the potential difference over C2, let's call it delta V2. Delta V1 and delta V2 has to add up to the total potential of the battery, delta V. So we have delta V equals delta V1 plus delta V2. Using the property delta V equals delta V1 plus delta V2 and replace delta V1 by Q over C1, replace delta V2 by Q over C2, we can find out a relation between equivalent capacitance for two capacitors in series. It's given by the equation 1 over CEQ equals 1 over C1 plus 1 over C2. When two or more unequal capacitors are connected in series, each plate will carry the same amount of charge, but the potential difference across each capacitor will not be the same. The individual potential difference on each capacitor would add up to the total amount of potential difference of the battery. We can use this equation to calculate the equivalent capacitance of arbitrary numbers of capacitors connected in series. When two or more capacitors are connected in parallel, the potential difference across each capacitor are the same. The charge on each capacitor is different and is proportional to its capacitance. The equivalent capacitance of multiple capacitors connected in parallel is a direct sum of individual capacitance. This example shows how we find out the equivalent capacitance of a number of capacitors connected in network. So we first find out the equivalent capacitance of 1 Faraday capacitor and 3 Faraday capacitor in parallel, which give us equivalent capacitance 4. We find the equivalent capacitance of 6 Faraday capacitor and 2 Faraday capacitor in parallel give us capacitance 8. Then we find 4 Faraday capacitor and 4 Faraday capacitor in series is equivalent capacitance is 2. 8 Faraday capacitor and 8 Faraday capacitor in series is equivalent capacitance is 4. Last step, we have 2 Faraday capacitor and 4 Faraday capacitor in parallel, which give us equivalent capacitance 6 Faraday. So from the graph A, we have 6 capacitors connected in network. After calculating the equivalent capacitance, we find the capacitance between point A and B equals to equivalent capacitance 6 Faraday.